Welcome back. So today I'm going to be talking about a little bit on friction and why we shouldn't think of it as this bipolar thing where it can either be static or kinetic in nature, but rather we should think of it as a spectrum of values that it can take. So to begin the discussion, I've laid out a box over here on top of a flat surface that happens to have friction. And the coefficients of said friction for the static and kinetic cases are μs and μk respectively. Now, if someone was to ask you, what is the frictional force exerted by the ground onto this box right now? I'm sure you'd say, there's nothing going on. Therefore, again, the box here has no tendency to go anywhere, and therefore, there is no friction exerted. To make this a little more concrete, I've put a plot over here on the side. We're going to keep track of the values of the actual friction exerted as we actually exert more force on the box. So in the very beginning, we got nothing. We are at the origin over here. But then if I exert a little bit of force, if I actually go ahead on my little box here and put a little bit of a force, let's say directed right now to the right, and someone asks you now what the frictional force is, assuming again we haven't broken the static barrier to start moving, you will tell them, yeah, there is some static friction backwards. And one thing that students typically miss is the fact that this static friction right now is matching exactly the force that is being exerted on this box along the surface here of the contacting surfaces, as you can see. So that will be the direction of the static friction right now, and it will match exactly what you're doing as the force. Now, again, this would look like, again, we're continuing along this plot in a one-to-one direction this way. And as we grow the force, right, as we grow the force, this static friction keeps growing along with us. So again, if we plot the behavior here on the plot, this just means that we keep on, every time we increase the force a little bit, the static friction increases in a one-to-one fashion. And then eventually we hit some kind of maximum where if I actually exceed right now this maximum, if I make the force bigger, this static friction can no longer support me, ergo I actually start to move and a different kind of friction applies to me. So once I cross this barrier, let's say that barrier right now for us is right there. Once my force again is growing to a point where it's going to actually exceed that barrier, we're going to switch to a different regime. I will no longer be actually still. I will start moving, and a different kind of friction is going to take over once I traverse this barrier. What will happen is this will now be kinetic friction, and it will be a lot smaller than the maximum static friction that we had just a moment ago. So we collapse down to a new state where we're moving now and we're only acted upon by the kinetic friction. And this kinetic friction is assumed to be constant now, no matter how much force I keep on pulling and putting forwards ahead over here. So no matter what the force is that I exert from this point onwards, this guy remains constant and unchanged. He just hinders my motion by some amount. So how would that look on our plot? That would mean that again, I reach at some point a threshold, that orange line that we saw over here, beyond which again, once I exceed it as the force, once I exceed it, what ends up happening is I turn around and I drop to a constant level of friction forever after. And the friction that I have down here right now, this specific threshold, will be the kinetic friction. This will be over here a line representing kinetic friction right now. So that's what I'm going to put in here. This will be FFK. Now for the top part, this guy over here is given a particular name when you're doing this in Mechanics 1. He's just called the maximum static friction, or FFS max. So again, I will call it that over here, FFS comma max. So you see the behavior of friction is actually linear at first, linearly increasing with our applied force between the two surfaces. And then once we reach that threshold, we quickly drop down into the kinetic friction zone, and then we continue forever after. So we're acted by the kinetic friction forever after, no matter what the applied force is. This to me and to you should look like a spectrum instead of is it a static friction or is it a kinetic friction question. So it all comes down to what the values of course, mu s and mu k are, as well as the particulars of the mass here of the object and how it is standing right now on top of this floor. Is it at an incline? What is the angle of that incline, etc.? Are there any other forces being acted on this box that would increase the pressure exerted between the box and the floor? All of these things need to be taken into consideration before we make a judgment of what is actually going to happen. So for this to make sense, I have an example lined up. So now that we know that the behavior of friction is actually a spectrum, I have an example lined up where we're going to practice just that and see that we could have 3 different scenarios from just changing the parameters over here of this simple problem. The problem itself just has a mass lying on an incline, and we're given the mass of the object, the incline angle, as well as the coefficients here of static and kinetic friction. We're not going to use specific values at first, but we're going to do them at the very end. We're going to see how 3 different parameter sets can produce 3 completely different outcomes right here. The goal of this question would be to find the acceleration of this mass m. And there are 3 cases that could happen right now. You could have, for example, that this box just does not move at all. And the net force that is acting along the direction of the contacting surfaces is less right now than the static friction that could be provided by the surface, in which case, obviously, you stay still. Then you could have the case where that net force down the incline here, along the incline direction, could match the actual static friction that can be provided, the maximum static friction that can be provided by this incline. In which case, again, you stay still, but you're at a very unstable equilibrium. You could very quickly, with a blow of the air, for example, just roll down the incline as you would. And then there's the third case where, of course, the F net force wins against the maximum static friction, and you get the box here to slide along the direction which it has a tendency to slide. So to see them, first of all, I need to identify the forces that are acting on this box. Obviously, we have gravity again over here moving toward the center of the Earth, so downwards. We've got the normal, which is a force, again, perpendicular to the direction of this incline. And to see things a little bit better, I will make a point free body diagram here on the right, just to see again how I'm going about solving this particular problem. So gravity here would be going again down. That would be mg. We've got the normal that would be perpendicular to that incline that we have set up over here, this dashed incline, and that will be the normal. And our incline angle can be translated into this diagram over here right now. Using the fact that these angles over here are opposite, I can make sure that I indicate that this angle over there is going to also be theta. And then what I need to do is realize again that I'm looking for the net force that is acting along the direction of the contacting surfaces. So along this direction, I want to see again if my maximum static friction will exceed that net force that is acting right now or not. So I am not actually going to put the static friction in my free body diagram right now because, again, I don't want to see its effect. I want to see the other creators of acceleration if they're going to actually succeed that friction. I want to compare what happens, what the rest of the things that are happening on this incline to what the friction is going to be that would obviously be acting here upwards and to the left. So without further ado, what I need to do again, I need to make an axis that points in this direction right now. You could choose the plus y and the plus x to be in opposite directions, doesn't really matter. Of course, you'd get negatives and nobody wants that. So I'll just keep it like that, very simple. And then we realize the only force that needs to be broken down is mg. So I do exactly that. I break it into components along the incline. And I notice right now my right angle for this triangle is right there for the components of mg. I notice that this angle right here needs to be 90 since it's the y and x axis being compared, which makes, of course, the angle on the very inside here 90 minus theta. And you can very quickly prove that this angle over here will also have to be theta because of that. So I have an angle to work with for the components of mg. Now, I go ahead and break this down into f net y and f net x. Now, when it comes to f net y, I know that I'm not going to be moving along the y direction in any case as the box. I'm not going to be moving like this at all. So I can very safely set it equal to 0. The forces, though, that are acting in the y right now, we've got a normal, and it's positive. The full normal is in the plus y direction. And then we've got a component of gravity that is acting again against that plus y direction. So we're going to have to make that negative. We have a negative over here. And this component, since the angle is adjacent right now to this side, will be nothing more than mg cosine of theta. And that allows us to very quickly obtain what the normal is going to be. Now, focusing on the x direction right now, the only thing that's acting there as per the diagram is, of course, just the force of gravity, but only the component along the incline, which in this case would simply have to be mg sine theta. Okay, so this is what's acting in the x direction. Now, I've ignored again friction because I'm comparing this f net x against it. So how do I do the rest of the problem here? Well, one thing I gotta ask right now is, what is the maximum static friction that can be provided by my surface? Well, for that, I am going to use the formula that I already know about static friction, especially the maximum static friction, which is nothing more than the coefficient of static friction times the normal. And I see that the normal right now has been determined for this incline problem, so I can actually plug it in and write my friction as this. Now, at the same time, don't forget, I'm trying to compare against f net x. So these are the two things right now that I really have to compare. And to do so, since I have these laying in front of me, I've introduced 3 parameter sets that are going to cause 3 different things to happen. And we're going to see again how we're going to treat each scenario now. So I'm only going to keep here the results. Okay, I'm only going to keep here the results. And I'm going to apply those parameter sets for the variables that you see. And see what happens right now. So we've got in parameter set 1, so I'll move these a little bit away. In parameter set 1 right now, we've got that our m is going to be 10. So again, I'm going to write down 10. I'm going to leave everything as a function of g because g is 9.81 and it ruins the nice numbers. And then I've got over here sine of pi over 4. Now sine of pi over 4 it's a special angle. It is exactly 1 over root 2. And this means right now that my net force in terms of g is exactly 10 over root 2 times g. Okay, now I can do the same over here and I can write, for the maximum static friction, I can write the coefficient, which is 1.5. I can write that as a fraction as 3 over 2. And then the mass itself is going to be 10, we said. We're writing everything in terms of g. Cosine of pi over 4 is the same as sine of pi over 4, which is 1 over root 2. And now over here, we see that I've generated here a number that is 15. It's being divided by root 2, and we write the g last. So what do I see here? I see that FFS max is going to actually defeat F net x, in which case the acceleration of our object is going to be 0 and it doesn't move. We don't go anywhere. And we can say again that the friction that is acting right now on the actual box is going to be exactly right now, exactly equal to that F net X. As weird as this seems, you'll say you just calculated that this is 15 over root 2g, and now you're telling me that it's going to match this. Well, this was the maximum that the incline can provide given the parameters that we have at hand. But the stress right now that the box is putting on that surface is only worth F net X, and that's exactly what the static friction is matching as per what we said in the beginning of this video. So that is what your friction here needs to be. It needs to be, again, 10g over root 2. So this is one particular, again, example, one parameter set that leads to this specific scenario. I can take a twist on this now and do another parameter set that does something else. Well, again, the only thing that remains the same are the two equations that I have here. They're not changing when I'm trying here the different parameters, but the treatment of the actual scenario will, the continuation will, these equations are always the same for all three parameter sets. So if I go ahead over here and try these right now, what do I have instead? I have a mass of 10 again, and an angle of 45, the sine of which is still 1 over root 2, which means, again, I have here 10 over root 2g. But for my coefficient of static friction, I only have 0.5 this time, which I can express as 1 over 2 to have it as in terms of a fraction. Then the mass here is still 10. We still have g as untouched of a constant. And then I have the cosine of 45 degrees, which is still 1 over root 2. So if I do this right now, I notice that these two numbers here get me a 5. I'm dividing by root 2, and I have a g slapped in the front here. And if you do the comparison this time, you notice that F net X actually over here succeeds FFS max. If you see this right now, we succeed actually FFS max. So what does this mean? It means there will be an acceleration right now on that incline, and we will calculate it, of the box, but also that the frictional force that is acting right now on that box is the kinetic friction. So completely different scenario as you see here. So how would you treat this if you knew now that this is the case given this parameter set? Well, you'd have to go back and steal over here the free body diagram that you made earlier, and now you would actually introduce the force of friction in it. The force of friction, we said no, though it has been determined now that it's going to be the kinetic friction, and of course it's going to be acting against the tendency of F net X, which was to drive the box down and to the right. So we have this setup right now, which we need to resolve. I hope you can see that in the y direction, nothing has changed, as this was added only in the x direction, which means that the normal coming from the y equations is still the same thing. Now, when we're dealing, though, with the x directions, we know that there's going to be an acceleration. And for the forces that are acting along the x, we have right now this x component of mg, which is mg sine theta, just like before. But this time around, this is getting dampened by the kinetic friction. And again, we can see why the negative sign, because this friction goes against our choice of positive x here. So all of this is equal to mass times acceleration. Now, I can open up the actual friction as the coefficient of kinetic friction times the normal, which you guys should already know. And then because I already have the normal from the stuff that I've done in the y direction, I can go ahead and plug it in. So I get over here mg cos theta to go in the position of the normal. Now all I have to do is rearrange for my acceleration. I notice that the masses cancel, and I can simply write this as, if I factor out the g over here on this side, I can write it as g sine theta minus mu k cos theta. And that is my answer for the acceleration that I'm going to be experiencing. As for the friction, again, all you need to do if you wanted to tell someone what the force of friction is going to be, you just have to solve right now what this is as a number. But I'm not going to do that because this is not what was of interest here. It was actually the acceleration that I wanted to find in this problem. So that is this scenario where, again, we had the net force exceed the static friction, the maximum that can be provided. And now the last scenario that I've got lined up over here, again, preserving the two equations that we've determined earlier. The last scenario, well, we take a look over here and plug in the values, we get 10 for the mass again, g is staying as is, and then we have sine of pi over 6. So again, if you don't know what the sine of pi over 6 is exactly, I can tell you that it's part of a special triangle, and you can see the angles over here. Pi over 6 has the smallest side against it, pi over 3 has the second smallest side against it, and then the 90 has the biggest side against it, which is going to be in this case here too. So sine right now of pi over 6 is going to be simply 1/2. This gives me over here a value 5g. Now, at the bottom for the friction, if we use the actual coefficient, which I've given over here in terms of a square root, so if we use the coefficient, this is around 0.5 something, if you simplify it as a decimal. But if I use it in terms of an actual rational number, and I plug in the mass, which is again 10, and then gravity, which I leave as a constant, and then the cosine of pi over 6. Cosine of pi over 6, we can see over here, is going to be root 3 over 2. So in this case, I've got cancellation of these two, and then these two here will produce a 5, so I got exactly the same answer as for f net x. And when you consider this right now, what happens when you're actually matching your static friction? Well, when you're matching your static friction again, you're not going to move. There's going to be no acceleration, and the amount of friction that is being acted right now on the box is exactly equal to f net x once again, or at this specific case where the two are matching, it's equal to ffs max. So you don't move again, and the friction that is acting on the box, if you were to answer that question, is equal to f net x or ffs max. So you can see again, three very different scenarios over here, three very different scenarios right now about what's going to happen if we have certain values for the parameters that we put on this simple incline problem. So again, I hope that this makes you understand that there's more into asking what is the force of friction that is going to act on a body, and we have to really sit down and actually think about what, first of all, what is the tendency of the object, where does it want to go? So when we determine the direction of the force of friction, in this case the tendency was down and to the right, so any friction that we found would have been pointing up and to the left. And then you want to determine, once you have the tendency and the friction figured out, you want to determine what is the net force excluding friction that acts along the surface here that the two objects are contacting through. So in this case, the incline. You want to see what is that F net along that direction. And if that F net defeats the maximum thing that friction can provide to you, you're not only going to move, but the friction that's going to be exerted on you is going to be the kinetic kind. If, on the other hand, your F net x matches or is less than the static friction that the incline can provide, you're going to stay stationary, and your friction is only going to match that F net x that is acting along the incline. So I hope you found this example helpful. Again, we will make some more of these in the near future. But for now, I hope you understand what we mean by friction acting as a spectrum. You now have a better idea of how to actually deal with questions that ask you about certain types of friction on certain situations where multiple forces are exerted. So I hope this helps, and stay tuned again for a future installment of another problem that we'll discuss further into this matter.